This is section 10.5. We're looking at this section in 2 different days, so this is part 1. We're looking at probability of independent events. So we have a definition again. You'll want to write this down in your notebook. Independent events means that the first event has no effect on the occurrence of the other or the second event. For instance, I could toss a coin twice. The first and second tosses do not rely on each other. So I toss a coin the first time, I get either heads or tails. When I flip that coin the second time, doesn't matter what I'm going to get. The second time I flip the coin has no effect at all on what happened the first time I tossed the coin. I could roll a dice. The first time I roll a dice, I have an equally likely chance to get any number on that dice. I walk over, pick it up, and roll the dice again. I could get any one of those numbers again. So rolling the dice the second time, that answer is not dependent at all on what I got the first time. Those are called independent events. And the probability for that will be conducted with this formula right here. Probability of A and B. Probability that both A and B will happen will be figured out by doing the probability of the first event multiplied by the probability of the second event. So it's known as PA times PB. This formula needs to go in your notes, and it also needs to go on your cheat sheet. And I would specifically write independent next to that when you put it on your cheat sheet. Probability independent. PA and B equals PA times PB. First example I want to look at with you comes out of your book. This is on page 717, and it's example number 1. For a fundraiser, a class sells 150 raffle tickets for a mall gift certificate and 200 raffle tickets for a booklet of movie passes. You buy 5 raffle tickets for each prize. What's the probability that you win both? So in this one, you're saying that the probability, or what is the probability that we win both, which means what's the probability that I win A and B? And in this case, A is the mall, and the second one was the movie passes. So what's the chance that I will win the mall and the movie? Well, if I use my formula, PA and B would be the chance that I win just the mall multiplied by I win just the movie. All right, so if we look back at the words again, we sell 150 raffle tickets for a mall gift certificate, 200 raffle tickets for the movie pass. When we figure out probability, remember our words are yes over total. My total is, it's not 200, it's 150 for the first one. So we have 150 mall raffle tickets, mall gift certificate, and we have 200 raffle tickets for the movie. And then we're going to buy 5 raffle tickets each. So my yes would be 5. 5 over 150 times 5 over 200. You can either reduce, or you can just multiply straight across and then reduce, but remember your final fractional answer should always be in the form of a reduced all the way down as far as you can fraction. This one comes out to 1 over 1200. In question number 2, what's the probability that we win the mall prize but not the movie passes? Mall prize but not the movie passes. So again, it'll be probability that I win the mall prize and is multiply. Remember the word and. This is a big one to remember. And means multiply, not movie passes. Well, if I have 5 chances to win, the word not would be the leftovers, which means I have 195 chances to not win. So it's the probability of the mall times probability of not movie. Mall prize, I still have 5 tickets out of 150. And then not the movie, we said would be the leftovers, is 195 out of the 200 that were bought. And then we do our multiplying again. So you can either multiply straight across the tops, or you can reduce each individual fraction, and then this one works down 13 over 400. 13 over 400. Your next example, in a survey at a football game, 50 out of 75 boys and 40 out of 50 girls said that they favor the new team mascot. If one boy and one girl are randomly selected, what is the probability that both favor the new mascot? So here's my clue. I'm looking for the words both. So I'm trying to figure out the probability that both people, both boy and girl, favor the new mascot. So if I use my formula, P, A, and B will be solved by finding the probability of just A by itself and the probability of just B by itself. And our A term is probability of the boy says yes, he likes the mascot, and the probability that the girl says yes, they like the mascot. And if you look back up at the original, it says that 50 out of 75 boys say yes. So that probability, exactly that fraction, 50 out of 75. Probability that the girls like the new mascot, 40 people said yes out of a total of 50. So this one is 40 over 50. And then you're just asked to multiply again. You can reduce your fraction as they stand. You could do your multiply across, and then just reduce to come up with your final answer. We should get 8/15 on this one. You might want to practice some of these reducing without your calculator just to see if you can remember how to do it. 40 and 50, you can reduce by 10. You're left with 4/5. 50 and 75, 25 goes into both of those, goes twice and 3 times. Now you can multiply across, and there's where your 8/15 comes from. Next one. A survey found that 46% of parents read to their kids at least once a week. If 3 parents are selected at random, what is the probability that all 3 will say they read to their kids? In other words, what's the probability that the first person says they read to their kids, and the second person says they read to their kids, and the third parent said that they read to their kids? Well, when we're dealing with independent events, and the key word here is and means multiply. So I need to find the probability that the first parent says yes, times by the probability that the second parent says, yes, I read to my child, times the probability that the third parent says yes, that they read to my child. In each of these cases, it says that the survey found that 46% of parents read to their kids, which means I'm going to use that 46% probability every single time. 0.46 times 0.46 times 0.46. And we can just multiply straight across, and we come up with 0.097. 9.7% would be our probability that all 3 of them said yes, that they read to their students. All right, so let's just do a very quick review for 2 of our large formulas that we have in this particular chapter. If you have one event going on only, not multiple events, but if you have one event going on, and you want to figure out the probability that A or B could happen, this was in section 10.4. Your formula, probability A or B, probability of the first plus the probability of the second minus any overlap, minus the probability that A and B will happen at the same time. Then we move to multiple events, which is what we're just talking about here, if they are independent. So this is your formula specifically for independent, that the 2 things do not affect the occurrence of the other. Probability that A and B will both happen is PA times PB. Now in section 10.5 part 2, we'll add in a third formula that will be the dependent formula. So we'll have 2 events that this time will be dependent. That comes up in section 2. All right, so that's it for this first half of section 10.5.